Okay, so we got a question right here. In a cyclotron in which Lorentz expression applies, protons were accelerated to a speed of 1.5 times 10 raised to power 7 meter per second. Determine the time taken to accelerate a proton to this speed from rest, right? Magnetic flux density is 1.6 Tesla, and accelerating potential difference is 13 K, which means 10 raised to power 3 volt, right? So there are two ways to do it, right? So I'm gonna do the first way. Okay, the first way, basically I'm gonna use the gain in kinetic energy is equal to total work done by the electric potential. Why I'm using this thing? Because as you can see, whenever they cross the d, right, whenever they cross the d, they're basically gaining the kinetic energy, right? Because the speed is increasing and increasing and increasing, right? So basically they're gaining the kinetic energy from the initial, like the initial speed was slow, now their final speed is basically getting higher, right? And why I said equal to total work done, because work done and kinetic energy are basically both equal. Work done basically W, because W, if you wanna be like, you can compare it by the the SI units. Work done has joules and kinetic energy has also joules, so basically they're both related to each other. And I'm using it because I need to, basically I'm just making shorter, right? In the electric potential, we need to know how much work done is done by the electric potential, the PD, the one we have mentioned before in the theory, that if it's in the right direction, the PD, we will get the high speed of the particles and stuff like that. So we're going to use gain in kinetic energy, right? Gain in Ke is equals to work done by electric, right? Electric potential, right? So gain in kinetic is final minus initial, right? So this is my final and this is my initial, right? U square, right? U is my initial, V is my final, and I know that work done, we have the formula which is W is equals to QV, right? So I'm gonna use this as QV. Okay, so this will tell me that how much work done, how much basically the potential, how much work done was done when they were switching across the D's, right? When the electric potential was helping them to cross across the D's, right? So yeah, so I'm gonna input the values. I have 1 by 2. I have mass, which is 1.67 times 10 raised to power minus 27. Is this the mass of basically the proton? Because in these we usually use proton mass, right? Or yeah. So, and we have the velocity as 1.5 times 10 raised to power 7, right? This is our final velocity that have been given to us. Yes, that have been given to us in the first paragraph, right? And then we're gonna minus it by 0, because before it was basically 0, it wasn't moving at all, it was just basically launched, right? So now we have n, we need to find n also, because we need to know how many number of turns are done by it, because see, as we move from here, this is one turn, this is second turn, this is third, fourth, fifth, sixth, we need to know how much turn is done by them. So number of turns, and then you multiply it by the charge, which is 1.6 times 10 to the power minus 19, and you times it by the electric potential, which is 1300, right? And please don't forget to mention the 2. Why 2? Because there are 2 D's. I just told you 1 2, right? For a full 360 circle, they have to go 2 times, one over here from this D to this D, and then from this D to basically this D, right over here. So it's basically 2, right? So you have to mention this 2, right? You can mention it inside or outside, it doesn't matter. I just mentioned it inside, right? Inside the brackets. So once you calculate all of this, you will get your final n as 45.2 orbits, right? Orbits means basically how much turn they did on a basically single time, single time how many turns they did. Okay, so now we're gonna need to calculate the total time because they are asked to determine the time taken to accelerate a proton to this speed from rest, right? Okay, from rest, so we have total time, right? We are going to use the Lorentz expression, which was total time, which is T is equals to 2 pi m by BQ. This formula is only gonna give me the total time for just one basically orbit, right? One orbit. We need to know the time for the whole orbit. How many times did the particle rotated before it was launched out of it, out of the day. So once you have written this for 45.2, you will input the value, so you will get 2 pi and you get m as this. M is basically given at the end of your basically exam paper, right? So yeah, I took it from there. 1.67 times 10 raised to power minus 27. This is the mass of the proton given at the end of your exam paper. So you have BQ that have been given to us 1.6 Tesla, right? And then you have given Q, which is 1.6 times 10 raised to power minus 19. This is the charge of the proton. Electron and proton basically have the same charge, so remember that. 45.2, and then your final answer will be 1.85 times 10 raised to power minus 6 seconds, right? So this is your T. Okay.